Can you see my screen?
Yeah, that looks good.
Thanks for the nice introduction. Hello, everyone. My name is Shashank, and I work in Condensed Matter Theory Group with Professor Shule Zhang at Case Western Reserve University. In this talk, I'm going to talk about how the Magnon transport influenced the unidirectional magnetoresistance in metallic magnetic bilayer. So, what is UMR? UMR is a kind of magnetoresistance that we observe in the bilayer of normal metal and ferromagnetic metal upon changing the direction of electric field or magnetization. So here we have a bilayer of normal metal and ferromagnetic metal layer. So when we apply an electric field, a charge current starts flowing. Now then, because of the spin Hall effect, spin current starts flowing into the perpendicular direction. Now, because of this spin polarization, we have spin accumulation at the interface, and this spin accumulation starts leaking into the ferromagnetic layer. Then we also have a diffusive spin current into the ferromagnetic layer. So this diffusive spin current affects the charge current into ferromagnetic layer. So now if we change the direction of the electric field, the direction of the spin current will also change, and so the direction of the spin accumulation. So that means the spin accumulation is also depends upon the electric field. So that's why when we calculate the total resistivity, it's not the same when we change the direction of the electric field. And the difference in this resistivity, we call it UMR. I will talk about the microscopic mechanism of the UMR in the next slide. So why we want to study the UMR? So effects like GMR or TMR, UMR can be also utilized in the data storage applications or the magnetic sensors. So the GMR-based devices, they are very complicated to make because the GMR, we observe GMR in a trilayer of ferromagnet, normal metal, and ferromagnet. So if we make a GMR-based device, it will be it's a three-terminal device, and it's also has a complicated structure. But if we make a UMR-based device, it will have a very simplified structure because we will have only one FM layer, and using two terminals, we can both read and write the data. So that's our motivation of studying the UMR, because UMR-based devices will be much simplified. But the problem is, for practical applications, we need a higher magnitude of UMR, but its typical magnitude is very small. So, and the role of the electrically excited magnons are largely unexplored in the previous studies. So, in this work, we study how the magnon influence the UMR, and we also propose some techniques to enhance its magnitude. So, let's look at the microscopic mechanism of UMR. So, in the bilayer system, if we write the charge current density into ferromagnet, it's given by this equation. So, the first part is Ohm's law, standard Ohm's law, and its linear response. And the second part is non-linear response, because we have a spin accumulation term here, which is proportional to electric field. So the whole term is proportional, it's proportional to Ex square. So that means if we change the direction of the electric field, we will have different resistivity and different conductivity. So we define the UMR coefficient as the difference of the conductivities when we change the direction of the electric field, divided by the linear root conductivity. So the dimension of the UMR coefficient is the inverse of the electric field, and it has a clear physical meaning. It represents a characteristic field scale at which our non-linear conductivity becomes comparable to its linear counterpart. So at finite temperature in ferromagnet, we have collective spin excitations, and we call them magnons, and they interact with electrons. But in previous studies, the interaction between these electrons and magnons is largely unexplored. So in this work, we not only study the electron-magnon interaction in the bulk, we also study their interaction at the interface too. So how this interaction takes place? A spin down electron annihilates, it creates a magnon and a spin up electron. And when a spin up electrons and a magnon annihilates, it creates a spin down electron. So in the bulk, we can write the thin film Boltzmann kinetic equation for electrons. These are well-known equations. So the first term is diffusion term, which represents how our distribution function evolves in space. This is a drift term, which tells us how our distribution function changes in presence of external forces. And on the right hand side, we have collision term. So the first term is spin conserving process, which is characterized by momentum relaxation time. The second term is spin flip scattering, which is characterized by spin flip relaxation time. And the third term is electron-magnon collision. And similar to electron, we can also write the Boltzmann kinetic equation for magnons. So since magnons are charge neutral, there is no electric field term here. We have just diffusion term. And then in the collision term, we have a momentum relaxation of magnons. And the second term is the thermal relaxation of magnons towards the global Bose-Einstein equilibrium. And the last term is because of electron-magnon collision. Now, after solving these Boltzmann kinetic equations, we arrive at the coupled electron-magnon drift diffusion equation. So in ferromagnet, the electron and magnons are coupled. So this is the continuity equation, and this matrix is spin diffusion length matrix. So the lambda is the electron spin diffusion length, and lambda m is magnon spin diffusion length, while the off diagonal terms arises because of the coupling. Now, when we turn off the coupling, these off diagonal terms will become zero, and our coupled system will reduce into the uncoupled system. And then we can also write the spin current. Uh, and this is also coupled where the ds and dm are electron and magnon spin diffusion constants. And these are off-diagonal diffusion constant, which comes because of the coupling. And in normal metal or non-magnetic metal, we have just electron. So we have just uncoupled electron continuity equations and the electron spin current. So we have this additional term here because of the spin Hall effect. So now if we solve the continuity equations in the ferromagnet, the spin accumulation will be coupled and it will have both characteristic electron diffusion length and magnon diffusion length. And in normal metal layer, we have spin accumulation in terms of only electron diffusion length. So we have actually 6 unknown coefficients. So now to solve these 6 unknowns, we need 6 boundary conditions. First 3 boundary conditions are very trivial, which says that magnon current will vanish at the outer boundaries. And the fourth boundary condition is the conservation of total angular momentum. And the last 2 boundary conditions are key boundary conditions because these 2 boundary conditions deals with the interfacial electron-magnon coupling. So first boundary condition tells us that the part of the magnon spin accumulation converts into the electron spin current. And the second boundary condition tells us the part of the electron spin accumulation convert into the magnon current. Where GME and GM are spin convergence coefficients, these basically characterize the conversion rate. So if we look at our schematic, so when we don't have electron-magnon coupling, we have a spin diffusion, a spin Hall spin current, which leaks into the ferromagnet, and we have electron spin current into the ferromagnet. But when we turn on the electron-magnon coupling, we can see that there is a discontinuity at the interface because of this boundary condition. And now we have both electron spin current and magnon spin current. So we can plot this spin accumulation and the spin current profile in the bilayer. So if we look at the curve, we can see that when there is no coupling, then we have a continuous spin accumulation throughout the bilayer, and spin accumulation decays smoothly into ferromagnet. But when we have coupling, then there is a discontinuity at the interface, and also spin accumulation decreases rapidly. Now our UMR is directly proportional to spin accumulation. And because of the coupling, spin accumulation is reducing. That means UMR will also reduce. So we can conclude that magnon plays a passive role in UMR contribution. That means if there is magnon, we have less UMR. So then we see the behavior of UMR as a function of coupling strength. So it makes sense when we increase the coupling, then the UMR will decrease because spin accumulation will decrease. And here we have like 3 distinct curves corresponding to 3 different magnon thermal relaxation time. So when the thermal relaxation time is small, that means the thermalization is faster. That means there would be less magnons to interact with electrons, hence we have more UMR here. But as soon as we increase the thermal relaxation time, the thermalization process becomes smaller, so that means more magnon interact with electrons, hence we have less UMR. And when we increase the coupling strength to a large limit, all 3 curves merge to a single curve because of the saturation of the conversion. The inset shows that in the inset we plot the UMR for different Magnon momentum relaxation times, and we can see that the curves are insensitive with the values of tau m, because tau m always conserve the Magnon numbers. So that means even if we are using the different tau m's, we will have the same Magnon numbers. So that means the same interaction. So that's why we don't have distinction like th like the thermal Magnon relaxation time as compared to the momentum relaxation time. So then we study the magnetic field effect. So when we apply an external magnetic field, the Magnon dispersion changes because a Zeeman term appears. So without a magnetic field, we just have this term and the gap term. And with magnetic field, we have this extra term. So AMS is Magnon stiffness, Q is momentum space, Magnon momentum space. This is Zeeman term, and this is Magnon gap. Magnon gap refers to the minimum energy required to excite a Magnon. So when we apply the magnetic field parallel to the magnetization, this term becomes positive, and when we increase the magnetic field, that means we need more energy to excite the Magnon. So that means if we increase the magnetic field, we need more energy to excite the magnons. So ideally, we will have less number of magnons to interact with electrons. So that's why our UMR increases with increasing the magnetic field. And when the magnetic field is anti-parallel to the magnetization, this term becomes negative. That means now when we increase the magnetic field, the overall energy will be less to excite the magnons. That's why the UMR decreases, because now there will be more number of magnons. So, and when the magnetic field is zero, the inset shows that if we plot the UMR as a function of gap, it increases because again, the energy required to excite a magnon increases. So now there are two ways to increase the UMR, either by increasing the magnetic field or or the gap. Then lastly, we study UMR as a function of layer thickness and temperature. So this curve has three different features. First, we observe a peak. Second, the magnitude of the peak changes when we change the temperature, and the peak position also shifts. So we observe a peak when the thickness becomes comparable to the electron diffusion length, because when the thickness is smaller, the spin accumulation cannot fully build up at the interface. And when thickness is very large, then there is the more electron spin current sent into the bulk. And the change in the magnitude, because when the temperature is high, we have increased population of magnons. So more interaction, that means less UMR. And the peak shifts because the spin diffusion length decreases with the temperature. So this is a summary of my main results. Thank you, and let me know if you guys have any questions.
So, thank you very much, Shashank, for that really nice presentation. I'll leave with a little bit of time left for questions, so I'll ask one of the ones that was in the chat. We have from Olivia. She said, in your boundary conditions, are G, ME, and GEM identical? And what would happen if they were or were not?
That's a very good question. They have different forms because GME is like it decides the conversion rate when Magnon spin accumulation converts into the electron current. And GEM is a rate for the electron, when the electron, how fast the electron spin accumulation converts into the Magnon current. So when they are like exactly equal, like in general, this term is bigger than this term. But when they are like exactly, if they are exactly same, then like we'll get the backflow, the same backflow of the spin current, and then the same spin current will again flow in the ferromagnet. So I think in that case, we will observe a very small discontinuity. Yeah.
That makes sense. Thank you. So if you please thank our speaker again. And I think there's a couple other questions in the chat. If you could reply to people as well, that'd be great. Thank you.
Thank you.